All right, let's get straight into it. Today, we're not just going to follow a manual. We're going to go deeper and learn to think like a real pro when setting up a VFD. We're going to take this Danfoss FC51 right out of the box and get it fully commissioned. And along the way, it's not just about what to do, but really understanding why you're doing it.
So let's start with the most fundamental question. Why do we even need these things? I mean, for decades, we just slapped a starter on a motor and called it a day. What's so wrong with just connecting a motor straight to the power line? It's simple, it's cheap, right? Well, the answer to that really gets to the heart of why modern motor control has changed so much.
And this, right here, tells the whole story. A direct online starter? That's like flooring the gas pedal in first gear. You get this massive, violent jerk. A huge surge of current floods the system, and that mechanical shock just hammers everything. Your belts, your gears, your bearings. But a VFD? That's the smooth operator. It gently ramps up the speed, it ramps it down, it completely eliminates that mechanical stress. And on top of that, you get perfect speed control, you save a ton of energy, and it basically acts as a personal bodyguard for your motor, protecting it from every imaginable electrical fault.
So, to put it simply, why is a VFD necessary? Because it gives you a level of intelligent control and robust protection that a simple on-off switch couldn't even dream of. It's all about making your entire machine smarter, longer-lasting, and way more efficient.
Okay, so we've got the why down. Now let's get our hands dirty with the how. We're starting with the absolute most critical first step, the power wiring. This is the foundation for everything else. You get this wrong, and nothing else matters. The consequences can be, well, explosive.
On the surface, the power connections look dead simple. You've got your incoming three-phase supply hitting terminals L1, L2, and L3. Then you have your 3 motor leads going out from terminals U, V, and W. Easy enough, right? But this is exactly where one of the most common and most expensive mistakes is made. And here it is. Burn this rule into your memory. You never, ever put a contactor, a breaker, or any kind of switch between the VFD and the motor. People do this all the time, thinking it's an extra safety measure. It's an old habit from old systems. But with a modern VFD, it's a guaranteed way to instantly destroy your drive.
So what's actually happening here? Why is it so catastrophic? Well, when that contactor suddenly opens while the motor is running, the magnetic field inside the motor collapses violently. Imagine stretching a huge rubber band and then just letting it snap. All that stored energy has to go somewhere. It creates this enormous voltage spike, an inductive kickback, that shoots right back into the VFD's output and just obliterates the sensitive electronics inside. It's an instant kill. And along with that number one rule, here are a few other critical safety points. First, for the same reason, never just unplug the motor while the drive is running. Second, physically separate your input power cables from your output motor cables. Run them in different conduits. This prevents electrical noise from the output from messing with your sensitive control signals. And third, and this is huge, make sure you have a rock-solid earth connection. It's not just for safety from electric shock. The drive's internal computer uses that earth connection as a 0-volt reference. A bad earth can cause the drive to behave in really strange, unpredictable ways.
All right, our power wiring is safe and solid. Now for the fun part, let's give this VFD its brain. We're going into the programming. This is where we teach the drive everything it needs to know about the job we're giving it, and most importantly, about the motor it's going to be controlling. The very first thing you have to do is input the motor's nameplate data. This stuff is absolutely non-negotiable. You literally take the values right off the side of the motor and punch them in. The VFD needs to know the motor's power, voltage, and especially its full load current. Why? Because all of its protective features rely on this data. If you tell it the wrong current, for example, it has no idea when the motor is actually being overloaded. Your protection is gone. Next up, we teach the drive how to run the motor, and we do that using something called ramp time. It's a super simple concept. You're just telling the drive how many seconds it should take to accelerate the motor up to full speed and how many seconds it should take to decelerate it back down to a stop. And getting this right is absolutely critical. Let's say you get too aggressive and set the acceleration time to just 1 second. You're basically demanding that the motor instantly overcome all of its own inertia plus the weight of whatever it's trying to move. It just can't do it. So it's going to try and draw a massive amount of current to compensate, and the VFD, doing its job, will immediately trip on an overcurrent fault to protect itself. A nice, smooth 10-second ramp, on the other hand, is gentle, efficient, and almost always the right call. Okay, so the drive knows what to do and how to do it. But how do we tell it when? I mean, the operator out on the factory floor isn't going to be opening the panel and fiddling with the keypad. They need simple, reliable buttons and knobs. That's what this next part is all about, wiring up the human interface.
For a basic start-stop push button, it's actually pretty easy. The drive provides its own 24-volt power supply on terminal 12. You'll run a wire from there through your start button, and then connect the other side of the button to the digital input for the start command, which is terminal 19. Now you also need a run enable signal on terminal 18. This is basically a safety check, so we usually just put a little jumper wire from the 24-volt supply over to terminal 18 to keep it active. Then you just hop into the parameters and tell the drive to listen for those specific inputs. So what about speed control? For that, we'll use a potentiometer. You can just think of it as a volume knob for the motor. It's a simple 3-wire connection. The drive gives you a 10-volt supply on terminal 50 and a ground on terminal 55. You connect those to the outer pins of your pot. The middle pin, the wiper, connects to the analog input on terminal 53. As you turn the knob, it sends a changing voltage, anywhere from 0 to 10 volts, back to the drive. Then you just tell the drive in the parameters, hey, when you see 0 volts, run at 0 hertz, and when you see 10 volts, run at 50 hertz. Simple as that. All right, moment of truth. Everything is wired. Everything is programmed. Now we have to move from theory to reality. This is the commissioning and troubleshooting phase. And this is where a good technician becomes a true professional. This isn't just about flipping the switch and hoping for the best. It's a careful, methodical process. You should treat this 8-step process like a pilot's pre-flight checklist. You do not skip steps. The most critical ones here? Double, even triple check your wiring before you apply power. And your very first test run is always with the motor disconnected from the machine. We call this a no-load run. This tells you instantly if your problem is electrical or mechanical. Only after you've confirmed the motor runs smoothly and, just as important, in the correct direction, do you finally connect the mechanical load for final testing. Of course, sometimes things still go wrong. But look, 90% of the time, it's going to be one of these 3 common faults. If you get an overcurrent, or OC fault, the first thing you check is your acceleration time. It's probably too short. If you get an overvoltage, or OV fault, that almost always means your deceleration time is too short. See, when you stop a heavy load quickly, the motor's inertia turns it into a generator, and it sends power back to the drive. And an overheat fault? Well, before you panic, just check if the cooling fan is clogged with dust. So we've gone through a ton of technical detail. Let's pull back and bring it all together. You can really think of a truly bulletproof VFD installation as being built on 5 core pillars. This is your framework for excellence. Here they are. Pillar 1, proper protection on the input with a good circuit breaker. Pillar 2, meticulously accurate motor nameplate data. Pillar 3, ramp times that are tuned perfectly to the mechanical load. Pillar 4, control logic, both your buttons and your knobs, that's configured flawlessly. And Pillar 5, a strict, unwavering commitment to safety, especially good earthing and using shielded cables. You build your system on these 5 pillars, and I promise you, it will be rock solid. And that brings us to one final thought to leave you with. How is it possible that a tiny, invisible change in a parameter, just adding a few seconds to a ramp time, can be the difference between a smooth-running factory and a catastrophic breakdown that costs thousands of dollars? It's because in those tiny details, that's where the engineering lives. So the next time you're standing in front of a drive, don't just mindlessly punch in numbers. Think about the logic. Understand the commander giving it, and really feel the engineering at work.